So in this video, what I'm going to do is that I want to show you how to simulate zeroth order, first order, second order reaction in a batch system. Then I'm going to do something a little more interesting too. I'm going to also model a case when you have these two pollutants A and B reacting with each other and then resulting in some pollutant C. Okay. Okay, so the first thing I want to do is basically you have in GIFMod you have these different components that we can use to build a model of water systems. They include a pond, plant, soil. A Darcy block is supposed to represent groundwater, and then you have this storage. You know, GIFMod was made initially for green infrastructure for stormwater management systems. So if you have, I don't know, an aggregate layer and so on, we can use that one. And if you have catchment and stream, right? Now we can use any of these for our purpose pretty much, but the most reasonable one at this time is maybe pond, okay? So the pond can, you know, behave just like a reactor. So I'm gonna add this pond, okay? And then what I'm gonna do is, let's say, you know, the pond is gonna have some water. I have to indicate how much water we have. And because it's a batch system, the amount of water is not going to change throughout my simulation. It's going to stay the same, right? So so basically, in order to indicate the volume, what I need is I first indicate an area. So basically, when you click on any of these objects, you're going to see this property window right there, and then there are some properties that we can change. So what I'm going to do is that I will indicate the bottom area to be 1. And then I will also indicate the initial water depth right there. You know, some of these you can't see, you know, the whole you know, phrase for the property, but you can actually maybe, you know, expand this table a little bit to be able to see. But we have initial water depth. So I'm going to say the initial water depth is also 1, right? So we have an initial water depth of 1, area bottom area of 1 square meter, and that gives us a volume of 1. Right? So you know what, by the way, let me just save this. I'm going to save this in my document. I'm going to save this as CE4565, okay? Or I don't know, maybe a better one, a reaction in batch system, okay? So that's what we have. You know what? Here's the thing. I can actually run the model right now, but I'm not going to see anything interesting, right? So basically, if you want to run it, all you have to do is, you know, there's this bottom called run model. I can click on it. And then it was very fast because nothing interesting happened. And I can look at some results. So this is not now I ran the model. You know, I can look at the storage, right? So how much water is in this pond? So if I click on that, what you see is essentially it was 1 when we started the simulation. The simulation went for 1 day. That's the default. We can of course change it, and then it stayed at 1 at the end, right? Because no water entered the pond, no water left the pond. We don't expect the storage to change, right? Now, next thing, I'm going to add these constituents. Okay. The first thing is let's do. I'm gonna do the zeroth order, first order, and second order reactions first, and then I'm gonna add this more interesting, you know, reaction that essentially that's multi-component reaction. We have 2 things that are reacting with each other. So in order to add first thing we have to do, we're gonna add water quality constituents. So I'm gonna click on this water quality item. And then I'm going to go to constituents, and I'm going to add 3 constituents, right? So I'm going to add a constituent. This is my first constituent. I can change the name, right? So what I'm going to do is that I'm going to call this pollutant 0. This is going to be the one that will undergo a zeroth order reaction. And then I'm going to do another one. And then this one, I'm going to go select it from here and then go to and change the name. I'm going to change the name to pollutant 1. Okay. This is the one that is supposed to undergo first order reaction. You can call it anything you want. You can call it A, B, C, X, Y, Z, whatever you want. PCB, I don't know, PAH, whatever pollutant you have, right? Or organic matter, oxygen, anything. Then at this time, GIFMod does not know anything about what those pollutants are. It's just creating some dummy, pollutants, and then we're going to tell what the properties of those pollutants are later on. And then the third one, I'm going to call it pollutant 2. Okay, this is supposed to undergo a second order reaction. Okay. And then what I'm going to do is next thing, so you have these reactions. I need to define some reactions for these pollutants, right? So I go to reaction, I click on this, triangle, and we're going to have, first of all, let's define reaction parameters, right? So essentially the reaction parameter that here we have is the decay rate constant K, right? But then the K, I'm going to have a K for pollutant 0. I'm going to have another K for pollutant 1 and another one for the second, for pollutant number 2, right? So then I'm going to just add, add a reaction parameter. So just right click, add reaction parameter. Let me do the 3 of them. Okay, so now I have 3 of them. Now I'm going to go change the name. So this one, I'm going to call it K0. This is supposed to be the 0th order. Okay, and then just like the example that I showed you, the value, I'm going to say, let's do this. I'm going to assign this value of 0.5. So and for all of them, I'm going to make it 0.5. So the reaction rate for all these, these 3 biodegradation reactions is 0.5. Of course, you know that 0.5 with different units, depending on what order we're using. So then we're going to do a K1 here, and I'm going to say, the reaction rate is 0.5, and then the last one, I'm going to call it K2, right? And then the value, I'm going to still say 0.5, okay? And we can, of course, change that later on. Let me save this to make sure if something happens, I'm not going to lose what I've done. Then, okay, so that's pretty much it, okay? Now, what I want to do is that I want to create a reaction network. Okay, this is very important. So basically, I'm going to just right click on the reaction network. Here I want to say, I have this first order, 0th order, first order, second order reactions, right? So I'm going to right click, and then I'm going to click on open reaction network window, right? So then when you do it, you're going to get a window that looks like this, okay? And this is where we create our reactions. So the first one, the process name is just a name. You can put any name you want. So I'm going to say 0th order decay, okay, or biodegradation. And then you have this column. This is the process rate, right? So the process rate is, in the case of a 0th order decay, is just simply K. Remember, actually it's K0, right? And then K0, so that's our reaction rate because it's a 0th order. So I don't need to multiply. So you can actually type an expression here. You can type a full expression here. But in this case, my expression is pretty simple because it's 0th order. It's going to be K0. Then you have, so then these 3 cells that you see here, they are stoichiometric constants. Okay, so essentially what I say is that if reaction, the first reaction is 0th order decay, proceeds by 1 unit, how much of pollutant 0, 1, and 2 will be consumed, okay, or produced, right? If they're consumed, I'm going to enter a negative value. If they're produced, I'm going to put a positive value, right? So then since I'm defining my reaction based on how much pollutant 0 is being consumed, I'm going to just type a -1 here, okay? And then reaction 0th order decay is not going to affect pollutant 1 and pollutant 2, so I'm going to leave these 2 empty. Does that make sense? Okay, and then I can add process. So this is what we have. Let's add another process. Okay, I'm going to do the same thing here. I'm going to have first order decay. Now, what is the reaction rate here? What do you think should be the reaction rate?
K1?
It's K1 times pollutant 1, right? Because it's first order. Okay, so basically we say K1 times the concentration of pollutant 1. And then the stoichiometric, again, I'm just going to consume pollutant 1, right? Then, okay, so that's pretty much it. Is that clear so far? Okay, then I'm going to have the second order. So let's do second order decay. By the way, this name, the name that you put on the processes, it doesn't matter. It's whatever you like, right? It's just, I just want it to be something that is descriptive. And then I'm going to have K2 times pollutant 2, and then to the power 2, okay? Or just to be on the safe side, I mean, to the power 2 probably will work, but just to be on the safe side, I'm going to say pollutant 2 times pollutant 2, and that's going to make it pollutant 2 to the power 2, right? And then I'm going to have a -1 right there. And that's it, right? So I got my reaction network for these three pollutants undergoing zeroth order, first order, and second order reactions set up, right? Let me save it again. And so the other thing I want to do is, the only thing that is left right now is initial condition, right? So so I haven't indicated how much of pollutant 1, 0, 1, 2 we initially had in point 1, is in pond 1, right? So so I need to do that. So I'm gonna select this pond 1, and then there's this item here called constituent initial concentration, right? So constituent initial concentration, you know, if you move your cursor on it, you can see the full you know, wording of the property. So I'm going to click on this oh yeah, I'm sorry, I have to click on this thing, okay? And then I'm going to say, okay, pollutant 0, don't worry about particle and phase, okay? I can talk about that later on. But let's say we have a concentration of 10 for pollutant 0 initially. I don't know, let's do 1. I just want to be on the safe side. So, and then pollutant 1 was initially 1, 2, and pollutant 2 was also initially 1, 2, okay? And that's pretty much it. So we had a 1 milligram per liter, let's say, of pollutant 0, 1, and 2 in the system initially, okay? So that's pretty much it. And then everything is set. Now, by default, if I run this, it's going to run it for 1 day, okay? And I'm going to keep it that way. But if you want to run it for longer period of time, all you have to do is go to settings, project settings, and then here you can change the simulation start time and simulation end time. In fact, you can choose real dates, okay? I'm not going to do it here, but you can choose real dates. Let's say from, I don't know, September 1st of 90 to whatever, okay? Then, so that's it. I think everything should be set unless I've missed something. I think I can now run the model and we'll see what we'll get, right? So I'm going to run the model. It was pretty quick again. Let's see what we get for the result. So now if I right click on the pond, you're going to see this menu showed up. It says plot constituent concentration. You can also look at the mass too. Now in this case, because our volume is 1, the mass is the same as concentration, right? So now if I look at the concentration of pollutant 1, this is what you're going to see. So you see the linear decrease from 1 to 0.5, right? And that's because the rate was 0.5 and we ran the simulation for 1 day. So we lost half of the pollutants. And then the other one is, let's do the pollutant number 1, which is undergoing first order decay. So you see this, not very clear, but this is supposed to be an exponential curve. Now, if I run it for 2 days, that'll be more interesting. But anyways, I'm gonna keep it. You know what? Let's do it for over 2 days. That's better. So you know what? Here's what I'm going to do. I'm going to say input number, and I'm going to change this to 2. Save it, and then I'm going to run it again. Then let's do pollutant. Now it goes to 0. No, pollutant 0 goes to 0. It basically finish everything we had, and that's what we expect to happen. And pollutant 1, and then the second order one. Okay, that's what we have, right? And you can actually compare them to each other too, by the way. Oops. So basically I can just copy maybe this one, put it here, copy this one, put it here. And this is the graph that you pretty much saw, right? Okay. So you can change the if you want the color of lines to make them, you know, distinguished from each other. Okay, so that's what we get, right? Makes sense? Everything good? So now let's do the next step. I'm gonna continue on the same model, but what I'm gonna do is that I'm gonna add these two constituents, constituent A and constituent B. Okay, they are reacting with each other, and they are basically their reaction. I'm going to assume that it's based on the law of mass action. That means the rate of reaction is a K times concentration of A times concentration of B. Okay, essentially this is what we're going to have. We're going to have an A plus B goes to C, right? And then the rate of reaction K is going to be the rate of reaction is going to be K times A times B, right? Put a dot here to whatever. So that's the rate of reaction. And then for the sake of simplicity, I'm going to assume that the stoichiometric constant is 1 for A, B, and C, right? So I know it's probably not very realistic, but let's say 1 unit of A is, when 1 unit of A is being consumed, 1 unit of B is being consumed, and 1 unit of C is being produced. Now in reality, that's probably never the case in a real reaction, but I'm going to keep it simple here, okay? So let's go back to here. Now I'm going to add 2 more constituents, right? I'm going to call this A. Oh, actually, I'm going to add 3 more constituents because I'm going to have C2, right? And then I'm going to call this B. And then I'm going to call this C. Okay, and then let's do the reaction. So basically, I'm going to have a K, another K, okay? So I'm going to add another reaction parameter, and here I'm going to call it, let's call it KAB, right? And the value, I don't know, let's say 2, okay? Then, by the way, you see this temperature here. This is actually Arrhenius factor, because a lot of the reactions that we deal with, their rate depends on temperature, right? So this is a way that I'm going to explain this later on, but this is a way of, you know, handling how temperature affects the rate of our reaction, right? Anyways, we got so here it is. We got the reaction parameter, and then let's go to our reaction network, right? So we're going to have this. I'm going to add this process. What happened? I'm going to add a process. I'm going to call this what do you call multi-component reaction. Okay, the reaction rate is going to be KAB times what? A times B, right? That was the law of mass action that we used. Okay, and then the stoichiometric will be what it will be. So for 1 unit of reaction proceeding, we're going to lose 1 unit of A, we're going to lose 1 unit of B, and then it's going to produce 1 unit of C, right? So this has to be +1, okay? So the stoichiometric constant for C has to be at plus, okay? And that's pretty much it. I'm just gonna close this, save it. Oh yeah, one thing that I forgot, initial condition, right? So I need to specify the initial condition for A, B, and C, okay? So now here's what I'm gonna do. I pick the pond. I just go here. I'm gonna say add. So let's say we had let's say we had, I don't know, 1 unit of A, okay? And then we had, I'm gonna make it a little interesting. Let's say we only had 0.1 unit of B initially, and then we had no C. So I don't have to indicate that. So we initially had no C in our reactor, right? I'm gonna close it. I think everything is ready. Now let's run it and see what we get. So I'm gonna run this pretty quick. Now let's see what we get. So now let's look at the concentration of A. So this is the concentration of A. Let's say concentration of B. And let's say concentration of C, okay? And I'm gonna overlay on top of it, overlay the graphs on top of each other, and because that will make things a little more clear. So I'm gonna copy B, paste it here. So this is our A, and this is our B, and this is our C. So let me make, change the colors so I'm gonna make C cyan. I'm gonna make B green, just green. There's no green. It's just a dark green or whatever. Doesn't matter. Okay. So so this is what we have. So A, it went. You know what? Let me the legend. Unfortunately, I can't. I can expand this maybe. Oops, we did something weird. Let's do this again. I think this will fix it. Whatever, magenta. Okay. So here's what we have, right? So we have A goes down to around 0.9. B goes down to around 0. And C goes up to around 0.1. Does that make sense? Why doesn't A go to 0? Why doesn't A go below 0.9? Anyways, let me stop the recording so that we can have a discussion. So let's see. Stop recording.